Hello. So today we are starting with basics of NLP, or this is the first topic of the week three, and let's start it. And we're going to start with text pre-processing. Okay. So even before we are working with any NLP data, right, like any text data, we need to pre-process it. We have to make it ready. Like whatever, even let's say if you're creating some food, right? So first you have to do a meal prep, right? Then you start cooking it. So, the meal prep is what you call text pre-processing in this case. So let's start it. So the first text pre-processing thing that we do is lowercasing. Lowercasing. We convert everything into lowercase. We don't want to deal with the case sensitivity of things. If somebody says cat with a small and somebody says cat like this, to a user, these two mean the same thing, right? A cat and a cat, it's the same thing. So we lowercase it so that there is no this complexity or there. The second thing that we do after lowercasing is tokenization. What's tokenization? So basically, if I have a sentence, I have a good dog, right? So we can't give this whole sentence as a thing to the any. I am not explaining anything. Like for example, we cannot pass a sentence into the model or something like that. So we need to break it into parts. Okay, we need to break this into parts. So these small parts are called tokens. So generally, what we do is that generally, what we do is that we break this into words like I will be one token, have will be one token, a will be one token, good will be one token, etc. etc. So we break each of them, the words into tokens. So this is called word tokenization. We can also have like a big paragraph and we are breaking it into sentences. That can be sentence tokenization. We can also have letter tokenization. We will separate every letter this time. We can do that also. Okay, so there are many things, ways to tokenize. So one like tokenizer that is mostly used in GPT is called the BPE tokenizer, that is byte pair encoding tokenizer. In BERT we use the word piece tokenizer. These are some specific tokenizers that are used. I'll just explain BPE in short, not in that much detail, how BPE tokenizer works. What it does is basically breaks down everything to a single letter thing. Let's say I have a dog, will be I have a dog, and then it makes n-gram comparison. What is n-gram? I have not taught you. We will learn later on. That's why I didn't want to get into BP, but in short, I'll explain it to you. So let's say we actually compare two different next to next letters. So let's say H and A never occur together. No. So let's say if I have this weight, I have a cat. So if you notice, I have a always occurred together. एक साथ they occur a lot. So this can be one token. So what they do is that they see what small parts are together most commonly, most frequently common. So they make that a token and the separate ones are just separate. So what this does is that let's say if we have a very random alert like where, or rare, something like this. Maybe this is an unknown word. This word does not exist. So it cannot be tokenized, right? That is the logic because we don't have the word in any corpus. So but in a BPE tokenizer, this will be separated into something like this. Let's say Ake, where, I. Because this they do it on most frequent thing. Now this thing I can't explain it to you in detail, but this is a rough idea of this. So this is of the second thing we did. So this is tokenization. After we have done tokenization, we do something called stop word removal. So let's say I have a dog. So the words have don't have that significance in this sentence. No. Me and dog. What does this signify? Okay, that means, let's say, no, I have a good dog, let's say. So me, the dog, and it's good. So out of this, the words I, good, and dog have a lot more significance than have a. So we remove the unnecessary words like have a, for example. So these are called stop words. The words like have, that does not bring that much context into the whole thing. So I, a good dog. So this is stop word removal. Now after this, we do something called stemming. What is stemming? So let's say there is this word. Let's say we have this word leaves. Okay, a leave. So both of these go back to their original word etymology source, that is leave, for example. Okay, so what we do is that instead of having the word, let's say, um I am taking a leave, I am leaving. So instead of word using the word leave and leaving again, because they bring the same context here, right? That I am taking not a leave, I am taking leave, as in what, I am leaving the room, or I am leaving. So I am leaving the room. It's the same meaning, right? So we, what we do, we track it down it to its original origin word, that is leave, and we use the word leave in the place of leaves, or leave, or leaving, anything. So this is what we do. This is called stemming. Okay. Now, let's say if we have a word lemmatization. We, after this we do lemmatization. What is lemmatization? Let's say we have a word called falling and fallen. We again go to its core word, whatever the core word was. Okay. Now, the core word here will be fall. So, what is the difference between lemmatization and stemming? There's one stark difference. We are doing the same thing. We are not doing the different thing. Instead of going back to its original etymological word, we are going to its closest meaningful word. So, fall is a meaningful word. Leave is not a meaningful word. For example, history is mapped to history. So this is not meaningful. History is not meaningful. But let's say if historical is mapped to history, this is meaningful. So this will be lemmatization and this will be stemming. So this is the main difference between stemming and lemmatization. Okay. So this is all about text pre-processing. How we prepare the text before we are going to handle it finally. Okay, so let's now start about word frequencies. Let's say we have two sentences, I like pizza and I do not like pizza. So let's first write them independently. So independently, what are the words? I do not like pizza. These are the independent words. So in my first sentence, what is the probability? No, in the first sentence, what is the thing there? So it's in my first sentence, it is there. I like pizza. So I will be 1, then it's 0, 1, 1. Second sentence, everything is there. So it will be all ones. So this kind of model where we are putting this one, what do I tell? Like if I give you this sentence, right? So what does this mean? This would mean I pizza. Okay, so this kind of a model which we are encoding every word with, like we can represent a sentence using like numerical values of zeros and one. This kind of model is called the bag of word model. Okay, this is a very basic kind of model. Now after bag of word model, now we are going to learn the TF model or the term frequency model. What does the term frequency model do? The term frequency model tells how specific a word is in that document. Document matlab the sentence only. The sentence is called also the document. So in this, what is the frequency of I? 1 by 3. What is the frequency of like? 1 by 3. What is the frequency of pizza? 1 by 3. What is the probability of do? 0 by 3. 0. So that's it. And here everything is equally probable at 1 by 5. So that is it. This is what is term frequency. So term frequency tells us how rare or like what is the probability of a word being in that sentence is. So this is what TF is. TF is the count of words in the document by the total number of words in that document. By document, I mean the sentence. Okay. Now let's talk about IDF or inverse document frequency. The earlier one was term frequency and this is inverse document frequency. The formula is something like log of total number of documents by the number of documents having the word. So let's say I do not like pizza, right? Wait, let me delete this. So I is in how many sentences? Two. Do is in one. I not is in one. Like is in two. Pizza is in two. So what do I have to do? The IDF is the total number of documents is always two. So it will be for I, it will be what? 2 by 2. Log of 2 by 2 is 0. For this, it will be 0 0.6, 0 0.6, 0, 0. Okay. So now if you notice the values that are more frequent are getting a value of 0 and the values which are more rare are getting a value of a higher value in IDF. So what my uh, TF tells us how important a word is and IDF tells us how rare a word is. So now if we combine both of these essences, like how important, these are like two extremes of how a word can be, right? So if we combine them, so TF, IDF, it gives us a complete picture. So TF, IDF formula is just calculate the TF multiplied by IDF. So this TF, IDF gives us a complete idea of how the word is, how important and how rare it is. It is giving both of the essence here. So you can calculate your homework or like assignment will be how find out the TF IDF for this example itself. So these are the three main word frequencies that we're going to play with and these are very basic. And now let's move on to the next part. Now, if you had attended our Transformers lecture, right? So we had talked about word embeddings, but I'll explain it to you again in short. So what word embeddings does is basically, let's say let me draw a 3D axis first. Okay. So basically it will try to place, wait. Yeah. So it will try to place similar kind of words together. Let's say this is the word king, right? The word king will be very close to what do you call it? The word, the word king will be very close to a man, but the word queen will be very far from both of them, right? So that is what word embeddings basically is. So what word embeddings can help us do is that they help us transform any word into a vector form. So basically, let's say if I have this word apple, right? So apple, I can write it as like 0.9, 0.1, 0.10, then 0.2, 0.3. This might be the embedding for an apple, right? So how can we do this? How does this learn the embeddings? There are two different ways of learning it. There are many ways, okay, but I'll explain you two. The main very famous ones are word2vec, glove, and fast text. Okay, so I'll just explain the first two in detail. Fast text you can see it in detail because not that much in detail. You know, you only need word2vec in very much detail. Glove is also not that much required, but Since it's a very easy thing, we'll explain it. So let's start with word to vec. So word to vec has basically two parts. One is called SIBO and one is called skipgram. So what is SIBO? It's basically a bag of words, but called a continuous bag of words. So what it does is basically, let's say if we have a corpus, right? So I don't know the meaning of life. So it tries to find the middle word. Okay. So let's say I'm just talking about SIBO right now. Okay. So let's say we have the word mm, five. Wait. So let's say we have the word the, and we have the word of. Okay. As simple as that. So now we what we do basically, it's just a neural network structure, nothing else. So we have a one hot vector for each of them. So what is a one hot vector? If you don't know, one hot vectors is basically we represent each word by zeros and ones, like the see the bow you did earlier. So I will have some, let's say I will be what, one followed by zeros. Next don't will be what, 0 1 1 1 1, something like this. So let's say how many words are there? There will be seven words, right? So this will be, what kind of a matrix will this be? This will be a 7 cross 1 matrix, right? This will also be a 7 cross 1 matrix, the word and the of, right? So now what we do is that we have a weight matrix here. Let's say this weight matrix has to be, let's say, we have to select a context window. This is called a context window. We are selecting three words at a time, right? So it will be the meaning of, right? We could have selected five. If it was five, what would it be? Know the would be the first two, then last two would have been of life, and we had to find the word meaning. So since we are selecting a context, this is called context window of size 3 here. So our weight size will be 3 cross 5. Okay. So we multiply the weight. This is my x, and then there will be an hidden state here, which I am not going into detail. The hidden state will be what? The hidden state will be nothing but the context size into the 1. So it will be 3 cross 1. So if it is a 3 cross 1, then it's what will be its weight size? The weight size will be whatever the not 3 cross. Why did I write 3 cross 5? Wait, 3 cross 7. 3 cross 7. Sorry. 3 cross 7. Right. So the weight here will be what? It has to be something into 7, 3. So it has to be 7 into 3, because my final has thing has to be, see, if I am multiplying weight into this, right, then my final output, whatever the final output would be, that has to be in the form of life, right? And so what is life? Life is nothing but 7 cross 1. So 7 cos 3 into 3 cross 1 will give me my 7 cos 1 life. Okay. So this is how the whole neural network model looks like. Okay. So this is the input, this is the hidden state, and this is the thing. This is how SIBO looks like. What SIBO does is basically find the middle word. Okay. This is how it's trained. Like it finds the middle word. And how does skipgram work? It's totally the reverse. I'm not going to explain this. It's exactly if I do this, nothing else. We give the middle word and it finds the rest of the words as surrounding it. The left word and the right word. If it was a context window was higher, let's say 5, then it would have what? Life would have given you know the on the top and off life at the bottom. So this is how the skipgram model works. So these two neural networks work next to next. Okay. And what happens is that this is how the word to vec whole thing it looks like. What happen with this, we generate the vector values that we finally get. These weight values help us generate the vector values. So this is how we use word to vec. Now let's talk about glove. Okay, so what glove does is basically, let's say we have three sentences, right? So let's say I enjoy flying. I love NLP. No, let's do it. I like NLP. I like deep learning. So we're talking about glove right now. Okay. So basically, from these sentences, what we build is called a co-occurrence matrix. We first select a context size again. So context size can be two words. Let's say enjoy flying, or I enjoy, or I like, or like NLP. But here we'll select a context size only of one, and we'll create a co-occurrence matrix. So this is inspired from CS224 only. So, and this is how the co-occurrence matrix will look like for this. So, see, let's say I like. So after I, there like, there are two occurrences. See, you can see there are two occurrences. Like NLP, there are only one occurrences. So like NLP, one occurrences. Okay, and it's two ways. So like if let's say I like is here, right? So if I like can also be in this direction also. So if you notice something, so if something is I like is 2 here and I like is 2 here, then this matrix will be symmetric. It's very logical, no? See, it's symmetric. It's symmetric. So, see, I think, yeah, I can show the symmetricity to you guys. Yeah, it's symmetric. Yeah, see, it's symmetric. So, this whole thing is called the glove representation. And when you do the probability of with this, like row wise, I find out the probability of everything. You find out the probabilities. So that is the final glove representation that we work with. This is a very naive explanation that I gave you of glove. Now you can also find out more about fast text. I'll attach some resources. And with this, the day one ends.